Lastly, let's get into molecular orbital theory. Lewis, Vesper, valence, bond theory, are models and really oversimplification of, orbitals or, wave functions. Being combined. A more, accurate picture, or, a more accurate way to describe bonding comes from linear combinations of atomic orbitals or LCAO, and that really actually produces, upon this combination, molecular orbitals. And that's the idea of MO theory. So if we kind of look at the idea, would be maybe looking at just something very simple in terms of an s orbital. S orbitals are spherical, and so going down to the lowest of the energy levels, right to the 1s, and then we could say that, in each, orbital here, there's one electron in each of these two different elements. But here's where we're talking about, this idea of, linear combinations of atomic orbitals. So we're going to put these two orbitals together in order to bond, right? In order to have a sharing of electrons. And so if we were to consider, each one, we would have now two bonding systems that would actually develop. One that looks like this, where we have a lot of overlap in between, and then one that looks like this, where it should be more like a pearl shape. There we go. Where there's, you can kind of see that they're pointing away from one another in terms of that relationship. So we have, two bonding scenarios that can happen here. We have our sigma bond, and if this is, in terms of, element X and element Y, right, we would have, basically good, overlap of those two orbitals, saying like we could have like X here and Y there, and we have, good overlap in between. And then if we go up top, we could kind of draw X and Y again. I'm going to give a little bit more space here. And this is what will be known as the sigma star bond. And notice that there's, no overlap in between. So what are these two, Now, differences, well, we have what's called the anti-bonding orbital, and we have a bonding orbital with these two different scenarios. So we have to, kind of remember that notion of wave functions going way back. Remember, this is going to result from constructive interference. Both wave functions are in sync. Which results in a lowering of energy. So if we look at that sigma bonding orbital, notice that we came down in energy to form it, and both wave functions are being cooperative with one another, and that's why we have this good overlap between the two elements. The sigma star is an anti-bonding orbital. And so this results from deconstructive interference. So you could say that both wave functions are not in sync. And so that results in a raising of energy. So when we put these two wave functions together, it's just like, waves at the ocean. Sometimes the waves in the ocean come in sets, and there's, a bunch in a different, a bunch coming in at the same time, and they all are in the same type of phase. They're synced with one another, and that's like your bonding orbital. And then if you've been on the water when it's really choppy and there's waves all over the place, well, that's really deconstructive, or that's the anti-bonding idea. So higher energy for the anti-bonding, lower energy for the bonding. So if I scroll up just a little bit, right, we see that, raising of energy right, in terms of going up. We also see, the other notion of that as far as the decrease in energy with it going down in terms of the bonding. So that's the idea of MO theory, is combining these orbitals in such a way where we have something that's productive, which is bonding, but then just, it can't be all productive. There's a bad side of it too, and so that's the anti-bonding orbital, which is, not productive in terms of bonding electrons. So we have what's known as bond order. And bond order is really an equation. Bond order is the number of electrons in bonding minus the number of electrons in our antibonding, and then that is divided by 2. If our bond order for a molecule, looking at, here simple diatomics for us, but if our bond order for a molecule is greater than 0, it means a molecule can exist. If your bond order, though, if it is equal to 0, that simply means the molecule can't exist. So it's this relationship. It's like kind of like being able to do predictive power. That if we have bond orders greater than 0, that means we have something that can be produced. It might not be something that's at this temperature or this pressure, but that doesn't mean that we can't affect, change in terms of the surroundings to make that molecule exist, right? Theoretically, it should exist according to the computational methods of MO theory. While we can then have, a bond order equal to 0, and that just is the opposite. The molecule can't exist. And the idea here is talking about, the lowering and gaining of energy, right? That if we think about in terms of, or if our number of electrons in bonding is greater than our number of electrons in antibonding, right? That means that this is favorable, that we have, these are of higher energy, and we could say that that is not favorable, while with the bonding set, these are lower energy, and that is favorable. So we want to make sure that, or I shouldn't say make sure, but for a molecule to exist, we must have this scenario, right? That we must have more electrons in the bonding. We have a net result of lowering of energy as opposed to them being equal. Right, because these elements are trying to do this to get to lower energy. So if the net result of sharing electrons or bonding, doesn't lower their energy, then they're not going to do it. So there are examples where we don't have certain molecules because of that fact, that it's just not a net lowering in energy of the elements. So they just actually don't do it at all. So let's look at a couple examples of MO theory here. With you start from the bottom up. Let's go to hydrogen. And if we look at our representation, normally we have our energy going up from bottom to top, and we're just writing in the valence shell that we have for each hydrogen atom. And in the middle, we're just looking at now the molecule. So when we bring these two orbitals together, each one has one electron in them, right? We're going to see a lowering of energy. and we're going to see a increase in energy as well. And it's going to be the same magnitude up as it is down. So here is our sigma and our bonding. And then up top is our sigma star and our anti-bonding. And we put electrons in, once, our bonding, anti-bonding orbitals are realized, put valence electrons in from lowest to highest energy, keeping in mind Hund's rule. For this idea of degenerate orbitals. So we put one electron in the bottom, and then we put our other electron in the bottom, and that is our MO diagram for hydrogen. If we were to calculate the bond order for our H2, we would have 2 electrons in the bonding, 0 electrons in the anti-bonding, divided by 2, we get a bond order of 1. Hydrogen has a single bond, and so a bond order equal to 1 implies exactly that there's a single bond in between the 2 hydrogen atoms. So that's one example. Let's take it to a few more here. Let's look at helium-2 and ask the question, does it exist? I mean, we know that H2 exists, hydrogen exists, but we don't know maybe helium. Diatomic helium exists. We know helium is a monoatomic noble gas, but could we make a diatomic out of helium? And this is what this bond order idea would allow us to do. Right? In each case, we have our 1s. Right? We're just looking at the valence shell for each helium atom. And then we would have the diatomic helium in the middle. So we would see a lowering of energy. We would see a raising of energy. Again, that occurs by the same amount to generate our sigma bonding and our sigma star anti-bonding orbitals. If we look at our electrons, each helium has 2 electrons in its 1s orbital. And when we now bring them together, we end up with now the same number of electrons in the bonding as actually the anti-bonding. So our bond order for helium would be equal to 2 electrons in the bonding minus 2 electrons in the anti-bonding, or have a bond order of 0. That means helium-2 does not exist. Let's do another example and ask the question, Well, I know diatomic helium doesn't exist, but what if I had a charge on the molecule? So does helium-2 plus 1 exist? So again, we would draw our 1s orbitals. We have the helium and its valence shell on both sides. And then we have the molecule that results from the bonding and antibonding orbitals in the middle. So same kind of setup every single time as far as this lowering and gaining of orbitals in terms of the bonding sigma and the sigma star, or the anti-bonding. One of these heliums would have one electron because we have this plus 1 charge to take care of, so we don't have the normal 2 electrons on each side. So I'm just going to pick one of the heliums to have lost one of the electrons, while the other helium possesses its 2. And we put these electrons into the middle, we find that, okay, now again I have more in the bonding than I do in the anti-bonding. So unlike helium-2, this molecule should exist if we calculate its bond order, where we would have 2 electrons in the bonding, 1 electron in the anti-bonding, and divided by 2, that would be 1/2. That means helium-2 plus 1 does exist. And it has been proven to exist as well. So while we don't tend to think about, half-order bonds, and for the most part we don't. We think single, double, triple. All this is saying is that there is a net lowering of energy in this setup with helium-2 plus 1. There's more electrons in the bonding than the anti-bonding, right? It's definitely a weak attraction, but it is a lowering of energy. And so that's why it is possible, and under the correct conditions, we can actually prove that it does exist. Do one more with the S before we get to now p orbitals. So lithium-2, does it exist? Well, all I'm doing here is just trying to go to another level, all right? So we're going to find this looks exactly the same as hydrogen. But what we do have to understand is, now we're not talking about the 1s orbitals coming together. We're really talking about 2s orbitals coming together in terms of lithium's valence shell of electrons. But you still see the same, the same idea as far as the lowering of energy for the bonding, the raising of energy for the anti-bonding. So we have our 1 electron in each one of those 2s orbitals for the lithium valence shell. And when we put those in the middle, we just have those 2 electrons in that sigma bonding orbital. So lithium-2 does exist. Right, and we could say that it would have a single bond between the 2. And this has actually been observed in the gas phase. So even though metals are pretty much monoatomic, save for Mercury. We can have diatomics, but we have to have the right conditions for that molecule. But here, theoretically, with the numbers, with the wave functions, the constructive interference with the sigma, deconstructive with the anti-bonding, theoretically we can say this molecule does exist, and then we can take that to the experiential portion and actually prove that it exists. What about MO theory now with p orbitals? So with p orbitals, we have two ways of orienting these. In one way, we kind of have a, head to toe relationship, if you will, where they're in the same plane, right? Notice that both the lobes are in that, in this case, I guess the X plane. And so you end up with kind of the same idea happening with the, the s orbitals, where you have here those nodes in the middle, where we're going to have a very large overlap in between the two elements. And then with the p orbitals, we have this little other piece to it. So we have a lot of good overlap. Between the elements. And I guess I should stick to my colors here. I'm sorry. So we have that good overlap. And then with the anti-bonding, it's right the same idea, just with the opposite scenario. Now you're going to have these lobes on either end, and then that little dinky lobe is going to be pointing in the middle. But as you can see, there's no good overlap there. So this is our sigma star, and this is our sigma. And these would be resultant now from two p orbitals, so we can be a little bit more specific now with our nomenclature, saying, because now we can make sigma orbitals not only from s orbitals, but now from p as well. Another way to see the bonding scenario for the p orbitals would be like a pi bond scenario. So another way to draw those orbitals would be not, end to end, but basically, both, right beside each other. And so we're going to find that we get the same type of relationship as far as overlap above and below now that we've observed with bonding and anti-bonding. So we would observe here the two lobes, and we would have this overlap above and below, just like we were drawing for valence bond theory. So there is our pi bonding. And I apologize up here, I like to keep colors coordinated. All right, we have our bonding with the sigma up there. And now we have the anti-bonding set up, which would be now kind of both those lobes pointing away from one another. Again, showing, not a good overlap. So here we have good overlap, above and below the elements. While here we have no overlap. And so that would be our pi star. So just like we have sigma and sigma star with the first connection, remember? Now with these other connections, with the pi connection, now we also have pi and pi star. And so as an example here, we'll find that there's actually kind of two ways to look at this idea of the pi bonding system. And we have what's known as SP mixing, which we have to kind of take into account. It really dictates how the 2s and the 2p line up in terms of our bonding and our anti-bonding orbital. So for nitrogen, and also diatomics or elements found to the left of nitrogen have this MO diagram. So when looking at nitrogen, I'm going to have to make a lot more room here. So we're looking at nitrogen, N2 in the middle. And if we look at the valence shell, well, we have our 2s and we have our 2p. And nitrogen has 5 valence electrons, so we have 2 in the 2s, and then we have 3 in the 2p. The S portion is, the easiest. It's the one that's going to always look the same. And so here we have, the lowering of energy, and then we have, a raising of energy for the 1s, right? So we have our sigma bonding, and we could be specific now of this being 2s. And then we have our sigma star anti-bonding, and again that would be our 2s, right? Bring the 2 s's together. We then have to bring together the 2p orbitals. So here's where we find a discrepancy between certain diatomics, mainly nitrogen and oxygen. For nitrogen, what we find happens is we have a lowering of energy for now 2 pi bonds. These would be the pi bonding for the 2p set, both of them. And then we have another lowering of energy, just not as drastic, to make this particular setup. And this would be now the sigma bonding. Again, for the 2s scenario. There's also then a raising of energy for then the anti-bonding set. So here at the top we have our sigma star for the anti-bonding, and then we have our pi star for the anti-bonding. So in kind of going, up from bottom, we have our, our sigma 2s. We have our pi 2p's, And then we have our sigma 2p as far as all the bonding orbitals are concerned. And then the anti-bonding orbitals, we have the sigma star 2s, the pi star 2p's, and then at the top, the sigma star 2s. So we put electrons in. If we count, we have 10 electrons. So 1, 2, 3, 4. Notice here that we have 100, 5, 6, 7, 8, 9, 10. So notice with those pi bondings, I put 1 in each before I started to pair them up. So there are our 10 electrons. And then if we are to calculate our bond order, for the nitrogen, that would equal 2, 4, 6, 8 electrons in bonding, 2 in anti-bonding, or a bond order of 3. And I think we can put together nitrogen as a diatomic and realize that we have that triple bond, right, which coordinates to the bond order. So that's one type of molecular orbital theory that we have for nitrogen and some other diatomics that are to the left of nitrogen. In particular, it's the sigma and pi, sigma star, pi star of the p set, which is what subtly changes. Let's do maybe 2 more examples. So let's look at oxygen. Oxygen has a somewhat different setup to our nitrogen. Similar in certain cases in terms of, the valence shells, in terms of the 2s and our 2p sets. But with oxygen, we actually have very small sp mixing. And this is similar with elements found to the right of oxygen. So like fluorine, for example, would be an example of an element to the right of oxygen. And if we put in our electrons, we have 6. So there's our valence electrons. And now bringing these together for the bonding and the anti-bonding, right, we would have a lowering of energy and a gaining of energy for the sigma and the sigma star. Here's our sigma bonding for the 2s, and then above it we have our sigma star for the 2s, and then we find just a different scenario for the MO diagram above. Instead of the pi's being below that sigma in terms of bonding, we actually have an opposite scenario here. I'm just going to bring this down a little bit. Where we have at the very bottom our sigma bonding. That's our 2p connection. We then have 2 of those pi orbitals So here is our pi bonding for the 2s. Above that, we have our pi star for the anti-bonding orbital of the 2s, and at the very top, we have our sigma star for the 2s as well. And so now putting electrons in from bottom to top. Again, remember our energy relationship going from bottom to top. We would end up with, 2 electrons in the star, our sigma star and sigma bonding of the 2s, and then we have now 8 more to actually deal with. So 1, 2, 3, 4, 5, 6, 7, and then 8. So notice that we have those 2 at the very top unpaired because of Hund's rule. And so this then allows us to determine the bond order for the oxygen. We have 2, 4, 6, 8 electrons in bonding. We have 2, 4 in bonding. We get a bond order of 2, which actually makes sense according to our structure of O2 and its double bond. So that's how you write MO theory for a lot of these diatomics, simple diatomics with s orbitals in their valence shell. And then we just got into some more complicated diatomics with p and s orbitals in their valence shell. But if you notice, all these examples have been of the same element bonding to itself. So these are all been diatomics in terms of nitrogen, oxygen, lithium, etc. So I like to finish off with one example where they're actually different. And let's look at actually a tough molecule to put together with a Lewis dot structure, which is carbon monoxide. Carbon monoxide, actually, while it's very simple, which is 2 elements, is actually pretty tough to put together. And so from Lewis, we actually end up with this as the structure for carbon monoxide, where our carbon is actually negatively charged and our oxygen is actually positively charged. Again, this is an oddball example because we wouldn't expect this with formal charge either, right? The oxygen should be negative, it's more electronegative. But this is, how we've come to understand carbon monoxide in terms of its structure, that there's actually a triple bond between the 2 elements, carbon and oxygen, and then we have this formal charge scenario occurring so that each have an octet. So both carbon and oxygen do have an octet. They are following that rule, but they're kind of, breaking the rules as far as this idea of formal charge. Let's see if we can use, this idea of MO theory to maybe, prove or disprove this idea of a triple bond between the carbon and oxygen, because if we were to put it together, we should get a bond order of 3 if that were the case. So let's see what we get. So if I have my carbon on the right, on the left, my oxygen on the right, and I'm just drawing the carbon monoxide, molecule in the middle. We find that they both have the same valence shells of electrons with the 2s and the 2p. Carbon has 4 electrons in that valence shell. Oxygen has its 6. And so when we put these together, we put them just like we did with the oxygen, right? We have this oxygen to the right, so we're going to write it in terms of it. Gonna bring these down just a little bit here if I can. So we have this lowering of energy, raising of energy. Again, there's our bonding and our anti-bonding set. So here's our sigma 2s. Here's our sigma star 2s. We then have our sigma 2p, our pi bonding, and then our anti-bonding at the very top. And so these guys should be kind of in the middle there. Sorry, just doing a little bit of editing. There we go. And so we have, all of these raising of energies for the stars or the anti-bonding, lowering of energies for the bonding. So here is our sigma 2s, our pi 2s with the two of them, and then we have the anti-bonding above with the pi stars, and then our sigma star at the top. So putting in electrons, we have 4 from the carbon, we have 6 from the oxygen, so that means we have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so there is our MO diagram for the carbon monoxide. And our bond order for the carbon monoxide would be our 8 bonding electrons minus our 2 anti-bonding electrons to give us a bond order of 3, which lends support to this idea of having a triple bond between the carbon and the oxygen. And so that's the idea of MO theory. MO theory is really the hardcore mathematics that is describing bonding. This is very, very complicated, and notice that I'm stopping here at 2s and 2p. We're not even getting into the idea of higher quantum levels, such as the third level and beyond, or getting into other types of orbitals like d orbitals and f orbitals. We can draw very, very, very complicated MO diagrams when we start to bring in the idea of those orbital sets as well. And then it gets even more complicated if we talk about different valence shells, oxygen being in this 2s and the 2p. How does that bond with sulfur in the 3s and the 3p? And so it gets very, very, very complicated. But this is where we'll stop with MO theory. You should be able to put these diagrams together with 1s's, 2s's, and 2p's, and be able to determine bond order and whether a molecule exists or not.